Hi everyone, good morning and welcome to the last day of this workshop. We have with us Cengiz Pehlevan, who will take us through the second part of his talk.
Thank you. I've been just flashing the resources slide from yesterday in case people want to take a note. What I talked about yesterday is covered here. And then I'll talk a little bit about more stuff covered here and some other stuff I'll point to. Okay, so yesterday we talked about basically, how to take limits and how to parameterize things in a way that like you end up with predictable scaling. It was mostly, I didn't give any, I gave some arguments about like how things should scale. It was mostly heuristics. And I showed a lot of simulation results. Today I want to do a bit more theory. So, okay. And the first thing I'll try to address is basically what happens in these infinite limits. Can we come up with a theoretical description? And that description, as Andre introduced yesterday, is going to be a dynamical mean field theory. I'll try to be, obviously, Andre gave a great lecture, series of lectures on this, and focusing on two-layer perceptrons. So I'll try to discuss deeper architectures and also point to results about other architectures as well, like ResNet-like architectures, and also transformers, attention layers. So actually, DMFT descriptions of these things exist. The caveat is, obviously, equations exist, but studying and getting insight from them has been a problem. I'll point to that. And also, I'll say that, okay, we'll get there. But just, I've been talking to people who have been asking about this method. So just to give you like a brief idea about what this method achieves, it's a powerful approach, I'll say, for reducing the equations of motion of high-dimensional systems. I said single here, but what I mean is a lower dimensional set of equations. And the mean field idea, the name mean field comes from is basically usually in certain contexts, this single particle ends up being some average quantity of some sort. And you might ask, why is this useful? Well, for two reasons. Mean field equations can be used to gain various analytical insights into the problem. Again, Turing lecture 3, right? Beautiful stuff that you can get from studying two-layer architectures. Also, equally important, these equations can provide computational gains compared to simulating the full high-dimensional system, right? Not always, but can be. And then also you might be able to use these mean field equations to come up with maybe alternative algorithms to solve problems and so on and so forth. There's both computational and analytical gains that you can get. Now, specifically for the context of neural networks, I think it's a speculative comment here, but I think there's another reason to look at these because, I've been showing empirical results about scaling the size of neural networks and that they give better and better performance. So if you believe that philosophy, then the limit of that is basically studying the infinite size models as the best model, the best performing model of a certain architecture. And, the DMFT is exactly that model. So, yeah. Okay, cool. So just to give you an idea of how this works, I'm assuming people might be familiar with like Ising-like systems, not maybe omit this first line, but look at the second line. But the idea is the following in any way. So we can think about basically a bunch of spins. In this case, I'll commit to the spins not being zeros and ones and just being spherical variables. Basically on a lattice, and they interact with some, coupling matrix, which I'll take to be random. Okay, so there is no notion of distance here. Everybody's coupled randomly. And the dynamics is governed by this Hamiltonian. If that doesn't mean anything, just look at the second sort of line over here. We're going to be thinking about basically some kind of Langevin dynamics. Okay, each spin variable here interacts with the other guys through this coupling matrix, plus some noise. Now you can see sort of the mean field idea here, right? The idea is that like what every variable here is seeing is sort of some kind of an average quantity of what's happening in the rest of the network. It's just these guys are added with some random weights. So you can immediately guess that in the limit n goes to infinity, this sum is going to turn into an average, and you're going to basically be seeing some kind of a mean field description. Okay, so many people, many famous physicists studied this problem. And basically, at the end of the day, what happens is you can take this random coupled system and write an equivalent system, okay, which I'll call this uncoupled in the limit as n goes to infinity. And that system is going to be given by this. So let's look at here. So notice that first I got rid of the I index. So I'm not thinking about a particular spin variable here, but just a generic random variable. So this t is a typo, so ignore this. Lambda is a constant. So the way this the dynamics of this s variable goes is basically through or the interactions of the spin variable with the rest of the spins is basically reduced to these two sort of terms. A noise term. This noise term is not white noise anymore. It's a colored noise that captures interactions. And also a memory term. This memory term is also something that captures interactions from past into the that get carried to the current spin through interactions with the lattice also. So, but the idea is the following, and of course, the statistics of this noise, the Gaussian noise, actually is also defined by the statistics of the S itself. So it's actually like a system, an equation that you need to solve, right? Because the left-hand side depends on the right-hand side, and this memory term itself depends on some kind of a response function or some kernel that depends on basically derivatives, and so on and so forth. But the point I want to make is basically this is reduced to the dynamics of this whole big system is reduced to a single equation of stochastic dynamics. And the relation between those, and again, Andrea made this point yesterday, I'll just repeat it, is as follows. In the limit, you can look at histograms of certain quantities over this lattice. Those histograms are basically captured by averages of, or basically the distribution of this stochastic variable across the noise. Right? So there's this, there's this map between them. So this is the idea. So reduce a large dimensional system into a single equation here. Of course, to make to capture all the effects of interactions, you have to introduce this like correlations and memory. So that's the idea. Okay, good. So how do you derive this? I mean, in physics, there's a bunch of methods that people use. We can write something called a path integral and do a saddle point approximation. There's a method called cavity method. Sometimes you can just guess and then try to prove and so on and so forth. I'm not going to go into the details of this, obviously, in this talk. But if you've never seen this and if you want a reading about this, there's a great, beautiful set of tutorial that appeared on Archive like just last month, a few weeks ago. I definitely recommend this as a great first read. It's very accessible, and it works through actually one exactly solvable model. So you can see the relation between these approximations and the exactly solvable model, and so on and so forth. What I'll do is basically see if I can apply this idea to neural networks. Okay. So, and the idea is here, we will think of this training as a high-dimensional system. Every weight is going to be, consider all the weights. The high-dimensional system. Is there a reduced description? Okay. Now, the reduced description I'll describe is actually will turn out to be not in terms of the weights, but in terms of pre-activations, but we'll get there. Okay, cool. And there's a series of papers we wrote about this. Obviously, I mean, they build up on the work by Andrea and other people and so on and so forth. And these all papers are all consider different architectures. I'll talk about this mostly, which talks about deep MLPs, and I'll just mention some things about ResNets and multi-head attention dynamics. Okay, so before saying anything, so this is just a fact. All right, so this is not taking a limit, this is exact. This is about gradient flow dynamics of an MLP. So this is following the notation from yesterday, but just to remind you, there's many indices here. So L here refers to the Elf layer of MLP. H vector is all the pre-activations in that layer. Mu is the index of a particular input. So this is a response of that layer to that. And T and S are two different times in gradient flow. All right, so I'm going to construct these objects. So this object is going to have, I'll call this a gradient, sorry, a feature kernel, because it's a dot product of basically feature vectors. Although, you know, it's not technically a kernel, but I'll call it this way. It has all these indices. And then analogous kernel I'll form from basically gradient signals. Okay, so what these are vectors that are derivatives of the last layer. So I'm thinking of the last layer as a scalar here to reduce notation. With respect to the pre-activations and an internal layer, there's a factor of n here that's for certain scaling arguments that we're going to do later on. We can also construct basically a kernel that carries this information about the gradients. So just I'll take you a second to look at this. All the indices clear. So mu and nu are data labels. So h mu here is basically means the response at a particular layer with respect to data x mu. That's what it means. There are different samples, yeah. So mu and nu are different samples. T and S are different times along the gradient flow. L is just a layer. Okay, so this is a lot of indices. It turns out these are actually important. Why? Because of the following. So if I were to write basically the gradient flow equation for how a network's output depends on a particular training point mu. Okay? Now this could have also been a test point, so I would have had to replace these by test points, but just for the notation I wrote it this way. That gradient flow equation just by just doing the chain rule, okay, can be actually put exactly in this form. So so what's happening here? So these are I shows the point that these are equal time. So these are t, 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 comma t, t, comma t, t, comma t. So if you knew these objects, you could just plug them into these equations, and you can track what the network's prediction should be for a particular input. Okay. So in a sense, they're sufficient, basically. There's another term here. This is the loss derivative with respect to the network's output. So suppose with a square loss, this will be just basically like a y minus f or something. So it doesn't. So you just need to know f itself as well. By the way, I mean, this is exactly the neural tangent kernel also. So actually, this is an alternative way of writing neural tangent kernel, if you know this. F is the neural network's output. Output, yeah. F mu. Okay, good. So these are important things. So if you knew these, you could actually, you don't, suppose someone gave you these, you don't have to even look at the network or something, just plug it here. You know how the training evolution works. So there isn't any approximation here. This is just gradient flow. Yeah. Yeah, so P is a number of samples. You can ignore this P. I put this before for certain thinking. This is just you can combine eta 0 and P into one learning rate. Yeah. I'm not going to scale P. P is just a data set. Cool. All right, so here's the thing. If I'm going to take n to infinity, you can see sort of a bunch of dot products here, right? So I'm just going to intuitively describe what's going to happen. Yeah. Yeah, so, okay, so there's a network, multiple layers. There's input x. This is the h vector at layer 1, h2. So the way I did this yesterday was there's a scalar HL, and this gets divided by a factor of 1 over gamma to give me F. So HL and F are almost the same. There's a factor of gamma, which I'll later vary. This was going to make me put into lazy versus which regime. Yeah, you could exactly. So there's just it's a factor of gamma if you want to carry or not. Okay, good. So the thing I want to say is basically, all right. So these are dot products of some quantities, you know, and like and every time you initialize this network, it will be, of course, a different path. And so these are actually, with respect to initialization randomness, these are random quantities. So if I take the limit n goes to infinity, okay, I'll just tell you what happens. It will turn out that basically these guys are going to concentrate and become deterministic quantities. Okay, sort of like the mean field kind of thing. They won't have fluctuations. And so let's discuss what happens. So I'm not telling you how I derive this result. I'm just telling you it's using one of these physics tools called the MSR path integral. It's a non-rigorous physics tool, so we don't have rigorous proofs, but I'll show you simulations in a second that verifies this. So what happens is in the n goes to infinite limit, these gradient feature and gradient kernels concentrate, meaning they're like scalars now, except that they evolve in time. The reason I'm emphasizing this is if you were doing this in the NTK parameterization, they will be static and they will not be evolving in time. In this particular limit, they do evolve in time. There's another factorization happens. So this is very like this factorization. Remember, I talked in the spin glass example, I was treating every spin as an independent sample from this stochastic process. Here, the analog things that basically factorize over sites and layers is basically these H variables. So the particular, so each of these guys become an IID draw from the same stochastic process as each of these guys that become an IID draw for the same stochastic process, as well as the gradient signals each of these guys see. So this is a bit different than the two-layer description that Andrea described yesterday. Correct me if I'm wrong, where the things that we're tracking were the weights themselves. So we're not going to have a weight description here. It will be the pre-activations, H's and G's that we're going to be tracking. Is that correct or not? Okay. 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 Cool. Could be good. So I'll comment on I'll comment on the two-layer version of this. So it's great if you could solve this issue. Perfect. Okay, good. So and the idea is basically, So the third idea is basically population averages over basically like averages over a collection of variables in the same layer, for example, will be replaced by averages over these kinds of distributions. So we're going to treat as a random variable that describes the distribution over whole of this. Long story short, I mean, I'll come back to the exact equations in a second, so we'll see. But I just want to point to another thing. The fact that like these variables concentrate means that actually the network's predictor also concentrates. What that means is the following. So the randomness we're talking about here, thank you for clarifying this, is so the data is fixed. Every time I initialize this network, I start with a different set of weights. Therefore, its training trajectory will be different. Okay. So I'm saying in the limit that n goes to infinity, that randomness still exists, but these quantities, the variance of these quantities goes to 0 with respect to. Does not depend on the initialization. Which also means that basically the predictor itself does not depend on the initializations. Okay. Good. So I will be able to actually plot this and compare to experiments. And good. Okay, so here's the set of equations that comes from this. A lot of stuff here. We don't have to. But I'll just try to break down what's happening. So let's see. So first these guys. These HL mu basically refers to a random variable that describes the statistics at a particular layer, okay, with respect to a particular input mu. And Z and G are some random variables that capture the statistics of the feedback signals, the gradient signals across the same. So these are random variables because, I mean, there's some randomness happening on the left-hand side. So let's look at those guys. So first, let's look at this mu, U, and R variables. So let's get this first U guy. So this U guy is basically a Gaussian process. Okay. And then, and its statistics is basically defined by these kernels, these phi kernels that carry on from the previous layer. So you see a bunch of terms here. If we ignore what's happening over here, basically, if this H was just equal to this, so just saying that H at every layer is a Gaussian process whose kernel derives from the statistics of the previous layer. If you know the Gaussian processes, like neural networks are deep neural networks are Gaussian processes paper, exactly covering that result basically. Okay, and now there's a second term here. There's a Okay, there's a second term here that captures effects that includes all these like memory terms and stuff. Lots of stuff going on here, so we don't have to go into the details of what's happening. But just the thing I want to point to is basically first, I mean, it's memory dependent, right? So this depends on everything that happened in the past. And it has this factor gamma 0 in front. And remember, the idea was that if I was taking this gamma 0 to 0, I was going to a lazy limit, and the gamma 0 finite was a rich feature learning limit. And this is also shown here. Gamma 0 is 0, recovers the Gaussian process NTK-like limit. And basically, gamma 0 finite is basically capturing everything that's happening. Okay, so we wrote this. Okay, what do you do with this? Okay, cool. But before answering that question, I want to point to a pictorial way of representing the same thing. So these HLs are again these random variables that depend on inputs and training time. So they're driven by some noise. Of course, the statistics of these noise depend on H's in the previous layers, and also response functions. Now, the response functions, because of the way gradient descent works, has this reciprocal property, right? Basically, so this is the same thing for G. The past G sort of affects what happens to H, and H basically affects what happens to G. So this is the structure of these equations. Okay, good. Okay, so what we'll do first is basically we can simulate actually this. So we were brave. We did the Monte Carlo for this. Basically, what that means is the way you would do this is you would sample a bunch. So everything depends on each other. So what you need to do is basically sample a bunch of Gaussian processes, plug them in, calculate these statistics. Using that, recalculate all these statistics of the covariances of the Gaussian processes, plug them in, repeat, and so on and so forth. Obviously, this is computationally very hard, so you're not able to do this for big thing. But here, I mean, we were able to do this, for example, a depth 4 bit 4000 network and synthetic data. So the biggest scaling with compute comes from the training time, but also the number of data is also scales quadratic with number of data. So let's see, this is just like a data set of 20 points or something like this. What we can plot is basically things like a loss dynamics. Okay, so the dashed, I forgot which one is which. Okay, the dashed lines are the DMFT solutions that's coming from this Monte Carlo procedure. And the solid lines is basically training the neural networks. Gradient flow with different learning rates, so different richness parameters. So this gets closer to lazy, this gets richer, and you did see a match. So remember, these histograms were the histograms of H were the things that our mean field theory was describing. So we can also compare that to mean field theory predictions. So this is basically the solid lines are histograms we made by training this neural network and looking at the last layer and then collecting all these, or in the way I described this, the one before the last layer, collecting all these H's and making a histogram out of it and comparing it to the statistics that you get from DMFT for lazier and richer models. Notice that the lazier guys look more Gaussian. That's what you expect. And then this is a similar thing for the feedback. In both training and Monte Carlo, you have some error. Yeah, I mean, it's true, but the error bars here are basically like, so that's important. So the thing here I'm plotting is loss. Loss depends on the predictor. So predictor is a concentrating quantity, so its variance is like 1/n. So with 4,000, so you don't even see it. That's the idea. And for these, again, we have 4,000 guys. So yeah. For the Monte Carlo steps, yeah, I mean, the Monte Carlo steps is itself, okay, yeah, so you have to do out of Monte Carlo as well. That's true. Z, okay, so Z is basically, Z relates to G. G is the gradient, so it's basically, think of it as a gradient. Okay, cool. And this is also comparing basically like experimental and final kernels. These are the things that are sort of concentrating in the theory, and we're comparing them to what we get from simulations, so you get a good match. So that's good. Now, of course, scaling this to anything realistic is a big problem. I was at some point hoping that basically this will lead to a more computationally efficient way of training neural networks. I didn't give up that hope, but not in this naive way. But we can talk about this. Let me just make some comments. Yeah. So I have a table about this. There's a scale which is I'll tell you after this, but for small data set sizes, actually DMFT is more efficient. But that small is basically like okay, I don't want to say something that's wrong, but not practical, small. But and then for a large number of data points, or if you're going to train longer, basically neural networks is more efficient. Off the record, but this is on the record, I believe that a neural network is actually a very numerically efficient way of doing this DMFT. So that's how I think about this. So that's how I think about this, yeah. Yeah, so there's that actually, and also more importantly, also training steps, right? So you have to calculate all these guys. That's also makes it even harder. Exactly. So exactly. Now again, off the record, but on the record, we're trying versions of this where we're trying to sort of like come up with the most Markovian approximations and so on and so forth. There's some success, there's some failures. We're trying a lot of numerical things to make this more efficient. I can talk about that later. Cool. Just to comment a few things. So this last sentence may not be correct as just underpointed, but for two-layer networks, it turns out some of these response functions disappear. And you can come up with like a nice PD-like looking thing. Maybe this may match what you have, so I have to work this out. For linear networks, actually, the DMFT closes under kernels, everything. So basically, you don't have to, you can give deterministic algebraic equations. You don't need to do any more Monte Carlo. You can solve these things. And two-layer version can be solved exactly, and it recovers known results in the literature about people working on linear networks. So I didn't talk about this, but I could give a DMFT for SGD. I just want to be clear about what I mean by this. I'm not going to do a data averaging or something. If you give me, like let's say MST or something, and divide it into certain batches, and give me that, I can write a sort of a similar like looking equation. Okay, it's just operating on this set of batches. The difference will be integrals over time become sums over discrete time steps, and at each time step, instead of summing over all data here, I'm going to be just summing over that particular batch, and you can do that as well. So there's no problem there. Good. Okay, so I could say much more about this, but I want to move to some different topic. I just want to. Okay, so this is what happens for MLPs. So now you might think of other architectures. For example, speaking informally about this. Suppose you consider residual network. What that means is now I'm going to introduce basically the next layer is pre-activation is going to go through direct connection and so a skip connection as opposed to the residual layer. Okay. Now think about what this is, what's happening, and I'm thinking of, let's say, as well as the infinite width limit, I'm taking an infinite depth limit. I put here a factor of L1/2, but for a second, suppose this was 1 over L. Right? This is like a Euler step. So basically what happens is in that case, in the infinite depth limit, you can define sort of a continuum depth variable and think of basically the evolution across depth as a differential equation. So in the case L1/2, which is more interesting, so this is like basically a random number. So you get like in the infinite depth limit, basically like a SDE that goes from network's beginning to an end. So the thing I'm trying to say is the following. In an architecture like this, if I took depth L and width N going to infinity in any sequential limit, meaning you can do this first or this first, what you can do is you can define index tau, which is basically a continuum index that tells you how deep you are. Okay. And then your equations now then get like some extra integrals over this. So now your stochastic variable H now has all these indices. X is for data, T is for training time, and tau is for depth. And the dependence on depth is going to be basically, in this particular case, basically a stochastic process. This is a Brownian motion over here. So and there's some deterministic operator here. So the full characterization of these equations can be found in this paper, which I'm going to flash in a second. I could flash it, but I would just have flashed it, so there wouldn't be any insights. That's why I'm not doing. And if you're considering, for example, multi-head transformer attention architectures, then there are other things that you could scale to infinity. For example, number of heads, number of infinite internal dimensions of these attentions, and MLP widths and depths. And for each of these scaling limits, again, you can write similar DMFT equations, again, using these non-rigorous physics space. I could flash them here, but that would be an equation that's showing all of this. And they're all basically shown in these papers. Now, for these architectures, we weren't able to do any Monte Carlo or anything. We were just able to write them down, but they are there. But what I want to do now is basically, instead of going more deeper into this, I want to say something about what does this theory imply for scaling laws, and this will be more empirical and so on and so forth. Any questions about what I've said so far? Good. Actually, I'm doing very good in time. much better than I expected. Yeah. Yeah.
Here, so you said there are various ways to scale up the slide after. So one question I have is, often I keep hearing that many of these big model sizes come because of the MLP more so than the attention, like all these. If you take any of these big models, often the large number of parameters come from because the MLPs are very, very big, right, more so than the attention layers or something. So I just wanted to ask if comparing maybe two of them, I don't know, like scaling MLP versus scaling attention. It's like you could think of like two other extremes. Does it reveal something?
Yeah, I mean, we do all of these simultaneously. So in these cases, so width and depth and all go to infinity. So I cannot say anything about that.
There's no way to like fix one of the.
You can certainly treat, like you can fix heads and head dimensions and scale those guys up.
Yeah.
For example, yesterday I talked about that, like how to scale width and depth.
Correct.
Exactly. You can also at the same time do these scalings. I'm not sure if you have fix these and do these, but that's also very doable. So you just keep these as architectures. But you're asking like a performance question. Is that what you're asking?
In terms of, do we see something any qualitatively difference in scaling one versus scaling the other?
I mean, well, okay, so not in, well, I mean, they just correspond to different limits in theory, but this is a deeper question about like empirically, is each parameter, the way each way you scale up a parameter, is it the same? For example, and this is an interesting question, so let me just comment since I have time. So if you look at, like, for example, Kaplan's scaling paper and stuff like this, usually, like when there's scaling, they say number of parameters, but like, what does that mean, right? And then, in some of these empirical studies, the way the scaling is done is through committing to a particular width and depth ratio. You're scaling up parameters in that way. And then that naturally raises the question, I mean, is there an optimal width and depth ratio? There is. And does it matter, like, if you scale width or depth, which one is more performant, and so on and so forth? Now, there are interesting published plots about this. For example, if you look at Kaplan's appendices, there's a plot that seems to suggest that, like, at least around the simulations they've done, if you increase width or depth, it's just not total number of parameters matter more than how you do it.
I see. Okay.
But I mean, in our hands, you do get like differences. They can create a situation where there's a big difference, and so on and so forth. So yesterday I showed a plot. I can recover that again. Okay, so this plot was actually trying to say something about that. What this is showing is basically was comparing some different parameterizations. So this was coming from scaling depth and width at the same time, and this was just thinking about considering width scaling. And this is looking at basically, as you change the number of parameters, the optimal width and depth ratio seems to change. Okay. And then what it's pointing is basically like the range of width to depth ratios within which the change in loss is up to some small percentage. So how tolerant you are, or how yeah. So basically, you see that like for these kinds of for the width and depth scaling of your parameterizations, the range within which you're tolerant to a larger set of width to depth ratios is bigger. So yes, there is differences in how you scale things.
Which model is this plot?
So this one is for the complete. This is the modelized. This is a transformer architecture.
Mm-hmm.
It's the last thing I described yesterday. Okay. Initialization skill. So I can point to, since you asked, I can point to like what happens. So for example, if you're
sorry, I think follow up question on the same thing. So there was this work a few years ago by Dan Roberts, Shoei Aida, and Boris Hanin, where they had looked at these infinite neural networks, but there they had the same idea that let's make it infinite, but keep the aspect ratio, the depth to the width bounded. So I don't quite understand what they did, but like, have you heard of this work, or do you think? So I think they wrote an entire book called Principles of.
Yeah, that's definitely true. I remember the books. I remember the book. I remember there's a chapter about this. I don't remember what they found, but I can comment to one thing about that book and how it differs from here. That book studies basically the NTK scaling, and the way they get feature learning out of it is by going, so in that scaling, you don't get any feature learning, right? So to be able to get that feature learning, you need to do finite size. You look at finite neural networks. So the way they get feature learning is looking at 1/, width corrections to the infinite width neural network. So this is a different scaling limit. So this is at infinite width, you still get feature learning. So this is one difference. One thing I can comment about this particular study is like, for example, so we talked about the idea that there are different ways you can scale things up, even the same architecture. Here, for example, if you're not careful with how you scale the internal dimensions of attention architecture, you might get something called attention collapse, meaning all your heads collapse to the same at initialization input. So you need to get some diversity. You need to be careful. Things like this. Many things can happen. Okay, so we don't want to go into this, but I want to switch gears about, say something about scaling laws. Okay, so let's look at the scaling exponents in these experimental papers. So this is a parametric form that Kaplan et al. Fit to their experiments. And this is the Chinchilla paper by Jordan Hoffman and colleagues that they fit to their experiments. In this particular plot, T refers to the number of training steps. These are like one pass online training. So data is seen once. And N refers to the number of parameters. It's not width, number of parameters. That's what this is. Cool. And NC and TC here are some constants. E is a constant. And they did fits, and they got some parameters that look like scaling exponents that look like this, which is interesting. Okay, so I want to point to one thing. This might be a total coincidence, but who knows? So the N here refers to number of parameters. So in these experiments, the width and depth were scaled with a fixed aspect ratio. So if you're actually looking the power, so of course the parameters go like linear. The parameters go like width squared, but then because the depth is also scaled with width, so actual number of parameters go like width cubed. So if I were to plot here at width cubed, so this number becomes very close to 1/width, basically. So, and that might have an implication. I don't know. We're going to talk about why that might be an implication. Okay, so this is a number of parameters, but if I was to think about width, this is actually 3 times that number. It's just some baseline. It's a constant. This is a parametric form that you fit to the, there's a number I don't remember. Yeah, irreducible error. Exactly. So these things saturate, you expect them to saturate. Kaplan et al. Did not have, so if you took n, yeah, so it sounds like they didn't have it. Yeah. I'm not sure. Is that true? You think? I don't know. Yeah. So I mean, they also have very different training setups and things like this. So in general, in my hands as well, this training, the exponents are not universal exponents. You know, different networks have different. Okay, good. So we talked about the idea that compute is important and it's proportional to n times t. Okay, so that's what you're gonna care. Okay, good. So let's keep this aside. You know, and there was a question to Andrea yesterday about like, you know, how do you approach, with what rate you approach to this mean field limits? Now, you know, things like loss and things like that. I mean, what you expect is basically, this is just like everything is like a central limit theorem kind of an argument, right? So you expect things to fall like basically 1 over n. Right? So this is a paper we actually did calculate these things and like basically looked at how things approach to their limits from finite size to infinite size, and that's basically 1 over n. So n being here, the thing that you scale, meaning width. So that's why I pointed to, I mean, if I were to plot here n, this is actually would be 1 over width, very close to it. Who knows? I don't know if this might be a coincidence or not, but that's another idea. Good. But okay, the point is though, I mean, I don't believe that's true. But let's think about the idea that, I mean, these sort of scaling exponents here are not 1. Okay. So what does this imply? So let's go back to these experiments that I showed yesterday. Okay. So so yesterday I also showed experiments where basically, you know, there was a lot of consistency in behavior, right? So basically, when I was scaling up neural networks, basically everything looked sort of same. But those were done with networks on simple data sets. Meaning like CFAR10 kind of thing. So if I have more complex data sets like ImageNet and Wikitext or something, so what I start seeing is basically some curves like this. Okay, so what's happening here is I'm again increasing the width of this neural network. Basically, you know, as you go wider and wider, of course, the consistency gets more and more. But you know, there's some deviations from basically this line, kind of saturation kind of an effect. It's like the E factor over there. I see the same thing in Wikitext as well. So what you can do is you can like do basically a scaling plot. So basically look at, you know, here, for example, and collect these points on a plot and plot it against n. Okay? And then look at what the scaling exponent is. So, you know, scaling exponents are here basically like 0.4, 0.6. They're not 1. Right? So basically what this is telling me is, you know, somehow whatever this regime is, it's not this 1 over n vicinity of this DMFT. I want to interpret it that way. Okay, good. Here's another experiment. I showed this briefly yesterday as well. So we were a bit more careful here. So this is, we were trying to study how to scale attention heads in this particular thing. So this is again a bunch of training loss, and there's a bunch of steps with respect to a different number of attention heads. And again, if you do the similar plots, early in time versus later in time, you see a similar picture, except that earlier in time, you're closer to this 1 over n scaling. Later in time, you deviate away from it. Okay, so it sounds like maybe you're closer to this DMFT over here. Maybe you're deviating out away from it later on. Okay, so how can we understand this? Or is there another sort of scaling regime which gives you this kind of a behavior? That's great. So, so that's what I want to talk about today. So I will not be able to address this in the full DMFT that I described, but I'll try to give you a toy model that has this kind of property. It will give us some insight. Okay, so, and this is work by, most of my work by my students, Blake Bordelon and Alex Atanasov. I mean, I'll present our versions of this, but there's a lot of works in this domain. The difference here will be basically like, including our work here, I'll have a dynamical picture. I'll talk about also the training dynamics as well. And then I'll mention a bit about feature learning as well. Okay, good. But that's just, and if you're interested in this, basically, this next section are basically reviewed in a blog form here, and then a much more deeper sort of review here. Good. Okay, so the insight or the new novelty is basically we now have to also think about scaling data size. Okay. So this is again like Andrea described yesterday. Okay, and then yeah, so we'll try to construct the simplest model which has these notions of data size, training time, and width, and we can see the trades-off between them. Okay, so here's the main ideas of the model. So I'm looking for a simple model where we can vary parameters, data set size, and training time. And for analytical tractability, I'll consider the lazy limit of neural network training. I'll comment on slight generalization to feature learning after this. In the lazy limits, I know that neural networks are kernel machines, NTK in the infinite width. Okay? So here's the main modeling idea. But for a finite width networks, they do also have empirical kernels, okay? But I mean, these should be some noisy versions of the infinite width models. Okay, so I have to come up with a noise model that sort of captures this noise. I'm thinking like a physicist here, I want to introduce some noise model. Okay, so here's so just to set up here. Just to set the ground, I know some facts. For example, let this K infinity be the infinite with NTK. Okay, it has a decomposition, a so-called a Mercer decomposition in terms of a bunch of functions. The idea that these functions are a complete basis, right? And then and they satisfy certain orthogonality properties. They're also eigenfunctions of the kernel. So what that means is basically and then the finite width model will have its own kernel and its own sort of these eigenbases and functions. So let's think of basically a finite width model. This will be my student, which is going to be learning a function that's going to be a linear combination of, x being the input of those functions. I know that basically because these guys are infinite, complete bases, I can expand these finite width eigenfunctions in terms of the infinite eigenfunctions. Let this AKL be those coefficients. Okay. So what do I know about this AKL? Not much. I don't know much. I know, for example, that in the limit that basically the size of this model goes to infinity, basically I should recover, basically this property. So what I'll do is basically try to sort of model this with a random matrix. Okay, so that's what I'll plug in. I don't know what A is. That satisfies this property. So I'll just plug in a random matrix over here and see what comes out. Okay, good. For teacher, I'll assume basically there exists a certain decomposition of a teacher model in terms of the features of the infinite width model. And then I'll commit to a particular data. So this is a teacher student model, so I'm actually now generating data. So X's will be sampled from some distribution. This distribution is the same P that goes in here. And there will be a function Y that basically described this way that generates labels plus some noise and so on and so forth. And I'm describing this matrix psi mu K. Mu index here corresponds to the data mu sample and K corresponds to the particular function that we're talking about. Okay, good. So just to summarize, okay, sorry, this shouldn't have appeared here. Let me just show everything. Okay, so the teacher model is this, the student model is this. So here I plugged in everything in terms of the infinite width features. And I want to consider a gradient flow on the MSE loss on generated labels based on the teacher and the student. And that basically boils down to tracking this quantity, the difference between these coefficients and those coefficients. And that's given by this quantity over here. Okay. Remember, I mean, so these are the weights with respect to the finite width features, and A is a random matrix that maps them together. Okay, good. And under gradient flow, basically what we're just simple algebra shows, the dynamics of this set of vectors basically follows an equation like this. And of course, this is a random matrix problem because these A's are random matrices and psi's are some random generated data. Okay. So long story short, what we can do is study a limit where we're taking the n to infinity here and the number of samples to infinity here and try to come up with a description of this dynamics. That goes through the path of again, a mean field theory, which I'm not going to go into the details for the people who know the technical details of this. We're going to assume basically these statistics are Gaussian. And the theory is there's a asymptotically exact limit with where basically technically what we could do is basically take m here being the dimensions of this infinite mix, already infinite, but basically the ratio n over m constant and p over m constant, and everything goes to infinity. I'll not present it this way. I'll assume that m went to infinity first, so this is already infinite dimensional, and p and n large, and the results are correct up to 1 over p, 1 over n. Structurally, they are the same equations, so if you don't like p, you can plug in alpha. If you don't like n, you can plug in mu. Okay, good. So there's a full asymptotic theory that describes dynamics, which I'm not going to show again. But what I'll discuss is basically implications of these equations in terms for scaling or loss. Okay. And for that, I need to introduce one more ingredient. Okay, so notice that I have to I didn't say anything about data, what I assume about the data distribution, what this distribution of this this was. Okay. So there we're going to look at the empirics a little bit. So this is true for many data sets. So what I'm plotting here is basically a rank-ordered eigenspectrum of the kernels of real data. Okay? So this is a ResNet on C55M. We take C55M, calculate empirically the initial NTK, and then basically calculate the kernel matrix, and look at basically the eigenvalues, okay, for different widths, for example. And basically what you end up seeing is like this kind of a behavior where you get a power law dependence on the rank of the spectrum. So based on this, we're gonna make an assumption, and these are called source and capacity constraints. This appeared in Andreas' talk as well, and appeared in many previous papers. We're gonna assume that the eigenvalues here, lambda k, fall with a power law in rank, and similarly, there's a power law in WKs as well. I'll show you an empirical test of this in a second. So there will be a plot that tests this. But basically, these are the two assumptions. And under these assumptions, you can show the loss behaves in the following way. Okay, so it's the three words you're seeing here: time bottleneck, data bottleneck, model bottleneck. What do these mean? So let's look at the time bottleneck. What that means is the following. We've given this data, this model, infinite amount of data, infinite amount of width, so it doesn't have any parameter constraints. So the only constraint is basically how much I trained the model. So basically what you see is then in this case, the loss purely or mostly depends on scaling with respect to time, which the scaling exponents itself derives from a combination of these things. In a second, I'll try to interpret what this is, but let's wait until there. Data bottleneck means if I took time to infinity and width to infinity, meaning I have a lot of parameters, I have all the training time I want, I'm just bottlenecked with data. As I keep more and more data, I get a power law in data. Again, this follows from the power exponent follows from here. And model bottleneck refers to the limit where I took training time and training data to infinity. So the only thing that basically bottlenecks me is my model's expressivity. Do I have enough parameters? And in that case, I get a power law as I keep adding more and more parameters. Okay, so I'll give you a very simple heuristic to derive these equations in a second. But before that, let me just show you that this model actually captures the thing that we talked about, the switching of scaling regimes. Okay, so here, every time I look at this plot, I get confused. So let me just take a look again. What we're doing. Okay, good. So here we're committing to a particular p is 1,000. So I have 1,000 data points. Okay, and I'm plotting as a function of time the test loss here, and then and I'm plotting models with different sizes of width. So this is a finite size model. So what you're seeing first of all is basically okay. So this curve over here, it gives me the curve for basically the this should be the n going to infinity curve, n going to infinity exactly. So this is the n going to infinity curve. This is basically telling me when I'm like just training time bottlenecked. And for all the other models, what I'm seeing is basically I start falling with some exponent and then some curve, and then I start saturating. Okay. So what's happening here is basically early in time. Okay, I have a lot of data. And I have enough parameters. So basically, I'm following the time bottleneck curve. But as I get longer and later and later, right, I have trained the network enough. The bottleneck becomes the width. So I go to a different scaling regime. So if I were to plot basically what happens as a function of n, the difference between LT comma n and LT comma infinity here, I'm following the 1 over n basically scaling, right? So here n is not a bottleneck, but later on, basically over here, now when the width becomes the bottleneck, basically the scaling exponent is governed by model's expressivity, and therefore I start seeing basically that power law over here. So the model transitions from being 1 over scaling to 1 over some other scaling law, but the idea is here now the expressivity has become a bottleneck. The model is not expressive now. But similar thing happens for P. Right? So P is a number of samples again. So I'm committing to a particular size, and I'm varying different data sets. So this is again gradient flow. Again, early on you're scaling with 1 over P, and later on you're transitioning to a regime where P is the bottleneck. Right. A training loss wouldn't saturate. Yeah. Cool. Okay, so this is the main intuition I want to give. So what's happening is when you're seeing this 1 over n scaling or 1 over p scaling, the idea is that's not the bottlenecking parameter. Okay, so this is like basically 1 over p you would see from CLT kind of thing. And this is basically when this becomes sort of bottlenecking parameter. Okay, so therefore you see a different scaling law. Let me just give you an intuition about where these powers come from. Yeah. Okay. It's very simple actually. Okay, so here's the idea. Now, because everything is square loss, okay, loss itself is going to be given by just like so if you do these limits, okay, what you see is here's what happens. Square loss, what happens is basically there's a critical k. This is the eigenfunction index, less than which you have learned everything, and above which you've learned nothing. Okay. Again, this appeared in your talks about these like spherical harmonics kind of thing as well. Okay. And then, when you didn't learn anything, the loss is basically the power of the function, right, for these modes that you haven't learned. So that's what that tail sum is. So the question is, where does this case star happen? Okay. So if you're data bottleneck, the case star is exactly the number of data points that you see. So every time you add another data point, you learn one more mode. So, and then the tail sum gives you the scaling exponent, scaling law. If your model bottleneck is the same thing, it turns out basically given the number of parameters, it allows you to learn basically a certain number of modes up to that K star. Beyond that, you don't have power to learn, so the tail sum becomes the error. And then the time bottleneck is basically same thing. You just have to understand that like because of time scales involved, and that those time scales carry like are modified by the power of the corresponding mode. So there's a basically K star goes like T to the 1 over B of this power. So again, if you plug that in here, you get the particular sort of K star, and the tail sum gives you the power. So this particular intuition is appeared actually early in a Spiegler et al. From Matthew Wiert's group. They had in appendices of their paper, they were looking at a static version of this, and then. But the same is true for this model as well. Yeah, right. Gradient flow, yeah. 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 Right. Yeah. Mm-hmm. These guys? Oh, except, well, okay. So what is So are you saying that, for example, I could just remove, just do a gradient and then think about basically a random feature model of that sort? I mean, the power laws derive from here. So there's an extra random matrix that needs to pass through. Right. What? Instead of IID entries. I have to think about this, but that could be true. Okay. Good. Anyway, so thank you for that comment. All right, so let's just put this in test. So what we're going to do is basically take a ResNet on CFR5M, and then we're going to do all of this at initialization. We're going to extract an empirical NTK. I'm out of time, or what do I probably? It just stopped. Yeah. Okay, good, excellent. So, okay, so yeah, so this is basically the eigen spectrum. Now we can also try to fit basically like these coefficients of the task from data. So the idea would be like you know, these are labels here, but you know, so this y is equal to w bar times the features, eigenfeatures here. So we can try to fit those w's, and okay. And it turns out that's very noisy. Instead, we fit basically like this sort of what we call this function over here, which is basically the tail sum. Rising a sum up to the kth eigenmode normalized by the full power. Anyway, so the point is, I mean, that guy doesn't look like, it should look like a power law. It doesn't look like a power law, but we could still extract, just fit a line, and then combine, get this constant, this number here and that number here, and from there plug into our formulas and try to make a prediction. So this is the test MSE as a function of compute. So I didn't show you the compute version of this, but once you have the N and T scaling, you can combine them to get a compute scaling. And then there are multiple models here. So the different colors are different widths. And then the difference between solid and dashed lines is this is in a lazy regime. So I chose my gamma 0 small, and this is in a feature learning regime. Okay. But basically the point is, you know, you capture somehow some version of the trend in the laser regime, but the feature learning regime is obviously different because this model doesn't have any, just working with statics. Okay, so I'll say W bar. Yeah, sure. So all right, so the first, our teacher is given by this K W bar A psi K X. So these guys, we calculate this empirically. Yeah, we just take the NTK, diagonalize it, and then basically then try to fit these guys from there. We don't directly, yeah, exactly. Technically, we don't directly fit these W's. Basically, we try to fit the power law that is. So that's actually what we do. Actually, sorry, yeah. Anyway. Yeah. Cool. Okay, so so we've recently done a version of this where we've said, okay, maybe let's try the first layer. Let's try to train the first layer weights as well. Because previously I had said that these guys are some random matrix. Now I'm going to let it evolve. So M is going to be, again, the features of the infinite width kernel. So that's infinite. N is going to be the layer width here. In the equations that I'm going to show, you're going to see B. In this particular version, we are also considering a mini batch, meaning at every step, we sample a batch of B from this underlying distribution. Okay, so what we get is basically scaling laws that's described by, okay, so this picture. So this picture is a bit complicated, so I'll try to work you through it. So what's going to happen? So first of all, again, we have a full description, but I'm just especially looking at the source capacity constraints sort of version. Basically, I'm assuming that lambda k falls like this. The tail sum falls like this of the teacher. Okay, and the main phenomenology that I want to describe is basically the difference between scaling exponent in the lazy regime and the scaling exponent in the feature learning regime. It turns out for this model, there's a difference for certain kinds of functions, and there's no difference for certain kinds of functions, meaning whether you put a network in the lazy regime or the feature learning regime, you get the same scaling exponent for certain kinds of functions. For other kinds of functions, you don't get any. You get a different scaling exponent, you get a benefit from feature learning. And that particular sort of, I'll call these functions that you're going to get benefit from feature learning, hard functions, and the other ones, easy functions. So what makes a function hard or easy turns out to be a very interpretable thing. Okay? It's whether this function itself is in or outside the RKHS of the initial NTK. And that, in terms of the equations I wrote, is basically boils down to a sum over these W's, and whether that sum goes to infinity or not. And whether that sum goes to infinity or not depends on basically this beta parameter over here. Notice that this beta is a property of the task itself. It's not a property of the kernel itself. So whether the task power falls slowly or very fast. If it falls very fast, easy function, you don't get a benefit, scaling exponent benefit. If it falls very hard, very slowly, then you get a benefit. So this is what it's showing. So for example, as n goes to infinity, the loss is a function of t, scales like t to the some power exponent. And this exponent depends on beta, so we're plotting beta. So this is the lazy exponent, and this is the rich regime exponent. Basically, you're seeing a benefit for the rich regime. You're not seeing a benefit for the lazy regime. You can even you can even draw phase diagrams as a function of alpha and beta. So this is compute optimal scalings. So they show basically like what parameter bottlenecks. You see like basically these scalings for hard and easy. And the arrow means what happens if as t goes to infinity. For example, in this regime, you start being time bottlenecked. And as time goes to infinity, you switch to being parameter bottlenecked, and so on and so forth. Okay, so there's a whole set of diagrams like this, but let me just show you some simulations. These simulations are basically exactly in the setting of the theory. So you want to see a match between dashed lines and like solid lines, which is simulations of neural network models. So for example, this is an easy task, meaning like the beta falls very fast, and like so we're looking at very large batch sizes and very large sort of model sizes. So we are mostly we should be bottlenecked by the gradient steps. And there's a scaling exponent, and you're seeing that like so gamma 0 is a very like lazy model. Gamma is bigger is a very rich model. All of these models basically fall with the same exponent. Exponent is the same, but there's a shift still. Right? So feature learning gives you an overall shift, but exponent is the same. And here, basically, you're looking at a hard task in the same limits, but basically you're seeing a difference in the scaling exponents with respect to t for the rich, so for the lazy, and the rich cases. So you see a difference. This model also has this sort of like a bottleneck transition. Like for example, you can start with, so this is a finite n as opposed to infinite n. As you're increasing n, later on, basically you transition from being t bottleneck to n bottleneck, and so therefore you get the n scaling law, and so on and so forth. This is all, yeah. This is synthetic data. I've generated everything the way I described things. Now I'll show you in real data. It should be, yeah, it should be. I haven't done this calculation, but it should be. But I can show you some simulations of, let's say. So now we're going to do something beyond what the theory has been designed for. Okay? So you want to design basically, you want to do experiments on ReLU networks on a single scalar input. And then basically, okay, and then yeah, so the way we basically like control the hardness or the easiness of the task is through basically changing the power here. Okay, and then so these solid lines are again simulations of a deep ReLU network. I forgot how many layers this was, but the beta here refers to basically is a function of the Q here, so it's a measure of hardness and easy. The point I want to make is, I mean, the scaling exponents we actually derive from the linear theory seems to match in the ReLU case as well. Okay, so in different cases, so didn't have to happen. That is interesting. So can we actually do the same thing on more real data? Okay, so I'll show you 2 experiments. So this is CNNs trained on MNIST. We again did the same thing we did before. We take the CNN, diagonalize it, look at the spectrum, basically extract all these eigenvalues and coefficients and so on and so forth. And then basically train for lazier and richer sort of scenarios. So this is the lazy scaling exponent we get from this theory, and this is the rich scaling exponent we get from this theory. Seems to match. That's nice. And here's an example where this doesn't match. So basically, this is a more complicated data set. So this is the lazy exponent from the theory, and this is the rich exponent from the theory. So you see a match up to some point, and beyond that, there's another sort of behavior here this theory doesn't capture. So this is the state of the art in this line of work. I mean, I look at this as success. I don't know, we're plotting real data, real networks. But obviously, there's still things that to be explained. Okay, so actually, good. So I'm just 5 minutes earlier. So the summary is basically, I mean, perhaps an obvious point, but I mean, here you see explicitly data structure and architecture jointly determine scaling exponents. It's also in these cases that feature learning may not always improve scaling exponents. This is true in the toy model, but in real data sets or the practical data sets that people care about, you'll always get basically some kind of improvement from feature learning. So it's interesting. So what is the implications about data sets given this? Are these data in some way hard? The way we describe that will be interesting to think about. Yeah, and then of course the models may transition between different scaling regimes during training, and we can see a clear example of this here as well. Okay, with that, I just want to thank my students, especially Blake, whose work, and Alex, whose work I've talked about, and other folks whose works I've talked about yesterday as well, and my current and unfortunately past funding sort of, sources as well. Yeah, thank you. I can take questions.
There are various interesting things one could do with this result, right? For instance, if you're given some data set, you could try and ask what is the architecture for which beta, scales in the right way. I mean, if you change the architecture, then you also change the value of beta, right?
Yeah,
so
I mean, definitely. So for example, if you take these like ReLU networks and go deeper, for example, these eigenvalue spectra change, and then so actually that's one experiment I was trying to do, basically making the same data set harder or easier by training for deeper
So that's one thing. I mean, could you even show that CNNs do better than just some fully linked network for the MNIST data set, or even something as simple as that, which is
I mean, it's exactly so that I'm exactly what I'm saying. So what would matter is basically the following, right? So what would change if I change architecture? Obviously, these eigen values will change. But also the task vectors, W bars also will change, because that depends in that case as well. So you could try to find a combination where our formulas give a better scaling exponent than a smaller scaling exponent.
Yeah. The case that CNN beats cases in which you can prove that CNN beats fully connected, these exist already.
Right.
Examples in which you can prove that CNN beats neural networks have been published already. That specific case, but generally.
Thank you.
More questions?
I guess you covered this already, but how did you get the WK bars for the test distributions?
Yeah, yeah. So, I mean, this is a linear algebra problem. So let's do this. So suppose I have a network, right? So I calculate the NTK matrix, right? So this is a matrix that's data, XX prime. This is all, I do this over the full data set. So this is a matrix that is P by P. I diagonalize it, look at the eigenvalues. Okay. So that's this matrix over here. And then basically, I remember, note that the index here is P, right? So this index here is actually it's a bit, sorry, this is W bar. Anyway.
So this is just with respect to the training data.
Yeah. I mean, it has. Are you asking me training versus test distinction?
Yeah. I mean, is there going to be a difference in WKs comparing train?
Yeah. I mean, okay. That's a good point. Yeah. So you can estimate these just looking at the training data, and you can estimate this looking at both training and test data, obviously. Right. I mean, okay. So it's a good point. Technically, there will be a difference. That idea will be different, and like people have written papers about this, but the difference will be small. So in this particular case, I believe we looked at training data. Sure.
The other question I had was about transformers. So if you think of transformers as taking some sequence of input vectors and providing an output, right. If you in the whole space, which is the tensor product of the entire of the input vectors for the entire sequence, this is probably a sparse matrix. The transformers, presumably, or many realistic transformers are looking at some kind of special structure in the sequence. Can this help to understand what are the kinds of data structures for which the transformer does well? I mean, a transformer is kind of, I think, at least conceptually somewhat different from a fully connected network, right? It's not just mapping all sequence to sequence functions. I mean, maybe it can theoretically, but it's often not doing that.
Yeah. Well, okay. So it is true. It's a more complicated architecture. I mean, but you can still define a linearized limit, and then there's a corresponding NTK which involves some contractions of these tensors, and you can go this path. However, I don't think that will be the interesting things that the transformers are doing.
The thing I was trying to get at, maybe this is just wrong, is that somehow it's a sparse function. I mean, the matrix, if you think of it in the tensor product Hilbert space of the input, is kind of sparse, right? It's giving you a very specific sequence to sequence mapping, and you have to work really hard to.
I'm not seeing that like. But which matrix are you talking about?
So let's say you have a sequence of n vectors.
Okay.
I mean, and every vector is coming from some dimension d. So in principle, the input is over d to the power n.
Okay.
But this is not, the transformer is not good at modeling all d to the power n to maybe it's giving you an output which is d. It's not good at modeling all those matrices. It doesn't have that many parameters. So it's kind of trying to capture some pairwise interactions between the vectors, which is different from all-to-all functions. And I'm wondering if this helps us understand why.
Yeah, I'm not sure about the parameter count, but anyway, could be. I just don't see. I don't know.
Thank the speaker.
Thank you very much.